All right, for worksheet B, starting off here with number 2. There we go. For chapter 2, so we're given two equations of two different lines. You got line 1 and line 2. It says they both are on the x-axis at points A and B, and then they intersect each other at point C. So starting off with just finding points A and B, if they are on the x-axis, anywhere you're at on the x-axis, we know the y-coordinate is 0 at that point. So if I take line 1 and I plug in a 0 for y, I'm looking at 8x plus 24 equals 0. And if I solve that equation to get x by itself, I'm going to get x equals -3. So that's one of our points. So for line 1, we're getting the x-intercept at -3. So we could write that as -3, 0. It does say find the coordinates, so we should write that as an ordered pair. For line 2, if I do the same thing and plug in a 0 for y, I'm looking at 4x minus 26 equals 0. So if we just solve for x, we'd be adding the 26 over to here. So 4x equals 26. Divide that by 4 on both sides, and we're looking at 26 over 4, which we could reduce to just 13 over 2. And so again, we would write that as an ordered pair because it says coordinates, so I want to write that showing both coordinates. So we'd be looking at the point 13/2, comma 0. So then to find point C, it says these two lines intersect at point C, so we're just basically solving a system of equations here to find out the solutions to the system for x and y. So for these guys, again, you could kind of just turn back to old methods. We could use elimination or substitution. If you watch the video for worksheet A of this chapter, we showed how to, on the calculator, find the intersection of two lines by graphing them on the calculator, so that works too. It's always good to know how to use your calculator and how to do these by hand, so you can do whatever the situation calls for. In this one, I'm just going to show this one by hand since we did it on the calculator in worksheet A. So for these guys, just solving our system of equations, elimination is a pretty good way of going on this. So I'm taking line 1 right here. I'm going to subtract the 24 over to the right just to put it into a more comfortable format that we're used to seeing. I'm going to take line 2 and I'm going to stack it right underneath so that my x's will match. I'm going to multiply line 2 by -2. So this would become -8x. This guy would become positive 10y. And this guy, if I multiply this by -2, becomes positive 52. I'm going to bring it over to the other side so it equals -52. And so now with elimination, I can just add my two equations together and let my x's get eliminated. So we're looking at 19y equaling -76. As we add those up, divide both sides by 19, and we get our solution for y of -4. And as always, if you want the other coordinate, we just plug that back in. We plug that back in for y in order to get an x value. It doesn't matter which equation you sub it back into, just pick one and plug it back in, and you get your x coordinate. So for part B here, so now they want a diagram that kind of represents all the information that we just found. So as you plugged in that -4 for y, you came out with an x coordinate of 3/2 or 1.5. So this was point C, so we got to make sure we show these two lines intersecting at that point, and we'll label it as point C. We're going to show the x-intercepts as points A and points B for these graphs. So we'll do a quick sketch over here to show both equations. So for line 1, we already figured out the x-intercept was at -3. And we saw that as point A. Just to help continue the graph of that line, I'm going to find the y-intercept as well. So if we sub in a 0 for x, so if I subtract the 24 and divide by 9, I can get a y-intercept for that as well. So if we do that, we're going to get -2 2/3 for the y-intercept. So I'm going to put that somewhere about here, and I'm just using that to help me draw the line. So helps to use some kind of straight edge for this if you got one handy, so that your line's a little straighter than mine. But there we go for line 1. We can now do the same thing for line 2. We already figured out the x-intercept for that guy. Was it 13 halves, or we could say 6.5 comma 0. So right there we found point B, so we got to label that guy. And then same thing for line 2. I'm going to get a y-intercept as well just to help me graph. So if I plugged in a 0 for x and I solve that equation, so I'm looking at 26 divided by -5 to get my y-intercept. So at about -5.2, I get a y-intercept for that one. So I'm kind of estimating here, but I know it's about there. So now we can draw our sketch through that one. Always good to label everything that you do on a graph. If you're ever doing a graph on a test, label everything. That's always really important. You even want to label the scale on your axes, just to show what you're counting by in case you're counting by something other than 1 especially. So that's an IB requirement for full points on any graph on an IB test, is to show the scale of your axes. So you always want to include that. We also figured out that point C was the point where they intersected each other. So we got that guy as well. So here's a sketch of what we got so far. So for part C here, moving down, they want us to find the area of triangle ABC. So we should just be able to use our 1/2 base times height in order to get the area of that triangle. So you can see the base of that would just be the distance from A to B. So if I do this value minus this value, I can get the length of the base on that triangle. So we figured out that B was at 6.5, 0. So that's our x value on him, and we saw that point A was at -3. So if I just find the difference between those, I can see the total distance is 9.5 units. And then as far as the height on that, that would be from the x-axis to point C would be our depth, or the height for that triangle. So we're just seeing how far point C went down. So if we look at our solution back here for part A, we saw that point C went down to -4. So we know this guy has a total distance of 4 units. And there we go. We can just plug that in and get the area of the triangle. So half of 4 is 2. 2 times 9.5 is 19. So that should be the area of the triangle. Anytime you're doing an IB test question, they always want to see units on that as well. So we'll just call it units squared for this guy. But that gives us the area of that triangle. So moving on to part E. Yeah, we skipped D. So we're moving on to part E here. All right, so for part E, so for the first part, so they're giving us this function here. We'll eventually figure out what P, Q, and R are, but we can tell it's a quadratic. So we know it's going to have the shape of a parabola. It tells us that A, B, and C, the points that we already have, are on that graph. And then it goes on to tell us that P, Q, and R are elements of the rational number system. So remember, rational numbers are any number that can be written as a fraction. So we know that's going to be true for P, Q, and R when we go on to find those in the last part. Solutions to this equation. So keep in mind, we don't know exactly where this parabola is yet, but if we were going to give it a rough sketch, and yes, this will be somewhat rough. If I would have done this on graph paper, this would be much more clear, but I'm just giving a rough sketch here. But anyway, if I'm going to try to create this parabola somewhat through those points, and we're getting something like this. So we got the parabola going through those points. Remember, the solution to any quadratic are the zeros, or the x-intercepts. So we already know the two solutions are the values for A and B. So -3 and 6.5 would have to be the two solutions that they're asking for part I. So now jumping on to double I, they're looking for the values of P, Q, and R. So real common IB wording here, they say hence or otherwise, meaning hence you can now use this information to get the answers for P, Q, and R, or if you see some other method for doing it, you can use another method as well. But this is kind of a hint to tell you that we can use this information to now do this problem. So that's what we'll do. So keep in mind the solutions that we just found, -3 and 6.5, if we were to solve a quadratic by factoring, we would be using those factors to get those solutions. So we know that within maybe two of the factors, since -3 was a solution, one factor would be x plus 3. And since 6.5, or you could say 13 halves, was the other solution, we know that x minus 13 halves would have been the other factor. One thing that we don't know is the value for p. And so that leading coefficient, we're just going to have to keep as an unknown for now. So we know our function initially is looking something like this. So if we do a little FOIL here, that's going to help us set up the next part of this. So if you FOIL that out, here's what you'd be seeing. So a little FOIL, so if we did our x squared as our leading term, then you got the -13 halves x plus 3x, so you could combine those together. Either use common denominators or you can use a calculator. Your calculator can do everything in fractions for you. So if we did all that, let's see, we'd be looking at our middle term, -7 halves x minus 39 over 2. So one more thing we'd have to figure out is now our value for p, and that's where now using a point on the graph can come into play to help us. So we used a and b to get those two factors, so I would use now point C to sub in some numbers for x and y so that I could solve for p. So we saw that for point C, the x coordinate was 3 halves, so I'm going to sub that in for x. I saw the y coordinate was -4, so I can sub that in for y. So we'd be looking at a -4 here, working on finding our p-value, and we said we were subbing in 3 halves for x. So it doesn't matter if you want to do that as a fraction or a decimal, whatever works for you on that. And then we're just solving that to get p by itself. So obviously this would be nice if we had a calculator to do this with. It just depends on the test that you're taking, whether it's a calculator or a no calculator test. Obviously if it's a calculator test, we would definitely want to plug that in and take advantage of doing it that way. But one way or another, however you solve for p, so you'd have to figure that out, divide it over into the -4 to get a value for p on that. So if we solve that, it looks like p comes out to be 8 over 45. So now we got our value for p. We just need to put it back into this format so I can figure out what is sitting here and what is sitting here as our constant for those values. So we just now can kind of go back to this line right here, and I can now replace p with 8 over 45. And we're just going to need to distribute that into these parentheses in order to figure out what the remaining values are that we haven't come up with yet. So if we distribute that in, sorry, here we go. So if I distribute that in, we're getting the darker color so you can see better. So now we're looking at 8 over 45x squared. If we multiply it into this guy, so we're looking at, 56 over 90. And then bring it into that last term. It's going to be -52 over 15 if you reduce it, which we would have to do for that middle term as well. So we can now see what's sitting in all those values. So now I can see that the p-value is this, the q-value is this, but we're going to reduce it because it does say in lowest terms. So we'd have to give a reduced version on that. And then we got our r-value right here. That comes out to be a positive with the double negatives. And reduce if possible because it does say in lowest terms. So for number 3, part A, they're giving us another quadratic here. Back in Algebra 2, we refer to this as vertex form, simply because you can look at this and get the vertex just by looking at it from the format that it's in. So when they want the coordinates of the vertex, I can see that it's at +4, -72 for the vertex. And the equation of the axis of symmetry, the x coordinate of your vertex is always the axis of symmetry, so we know that it's at x equals 4. Do notice that it does say the equation of the axis of symmetry, so you got to write that as an equation. If you just put 4, you would get it wrong. So, really important that you always pick out the details of the wording of the question. It's always going to be important for everything that we do in this class. So, moving on, find all the x-intercepts and y-intercepts. So, as we've already seen, intercepts are zeros. So if I want the x-intercepts, I plug in a 0 for y. If I want the y-intercept, I plug in a 0 for x, and then we just solve from there. So we'll just start out by plugging in a 0 for y and solving for the x-intercepts. So if I had y equals, let me go darker for you. So we got our y equals 5 times x minus 4 squared minus 72. So we're just solving that equation. So add the 72, divide by 5. We would then square root both sides. And then if I add the 4 over, we have our x-intercepts right there. On every IB test, the directions are always the same as far as how you write your answers. The standard directions are you can write your answer in exact form, or you can round it to 3 sig figs unless the directions say otherwise. This one doesn't specifically say how to write the answer, so we would either accept the exact answer, which I wrote here, or you could write this rounded to 3 sig figs, and that would be acceptable as well. But you got to stick with those directions. If you round it wrong or do 2 sig figs or whatever, anything other than those standard directions, you're always marked off a half a point on a test for that. So really important that you kind of stick with those all the way throughout the year. As far as getting the x-intercept, or sorry, the y-intercept, now we would plug in a 0 for x. So we'll show that one here real quick. So plugging in a 0 for x. And just solving from here. So we're looking at -4 squared, which is 16. 16 times 5 minus 72 is going to get us. So 80 minus 72 gives us 8. And there we go, we got our y-intercept. So moving on to the third part of question A. So write the equation of the graph in that form. That just simply means to expand this. So we're just kind of reformatting. So if I FOIL, distribute the 5, bring in the -72, we can reformat it to look like this. So if we FOIL that, I'm going to be looking at 5 times x squared minus 8x plus 16 minus 72. So bring in the 5, subtract the 72. So now we got into that format that they're asking for. So they're now asking us to use the information to make a sketch of the graph. So we'll give kind of a small rough sketch on what we're seeing for this one. So for this one, remember we found some intercepts already. So we figured out the y-intercept was at +8. So I know I got 1 point right there on the y-axis. We found the x-intercepts. I had left those as a radical, so you'd want to see those as a decimal probably in order to kind of properly place them appropriately on the graph. So we had one of them at about 0.2, so real close. So I'm going to put a 1 right there just to help scale the graph. And the other one was at about 8, or close to 8, or just shy of 8 on the other one. So there's 8, and it was just shy of that. So I got some intercepts right there. We also pointed out that the vertex was at 4, -72. So at 4, try to place that as best as I can. -72 obviously would be way down low. we would see something about here. So as far as our rough sketch, we had all that information. So something like that. Obviously, if we're using graph paper, that's going to be a lot prettier as we do that. But remember, you always want to label all of your numbers. So it's really important that you show appropriate scales and values. Obviously, you know, this is not a real clear scale that I'm using right here, since that was 8 and that was way down at -72. But always kind of at least show the values in a sketch. So now for part C. They're asking us for just kind of some transformation information to figure out what we can get. This one's a little tough, so let's see if we can work through it. But they're giving us now a second function, calling it g, and saying it's that x squared. So keep in mind, x squared is the parent function. So it's like, you know, if you were looking to go from the parent function to here, right, we were recognizing you'd have a scale factor, a vertical stretch at 5. We move 4 units to the right, so +4 was the horizontal shift, and -72 was the vertical shift. But keep in mind how this is worded. That's important. So it's saying this graph can be obtained from the other graph. So they're calling this one curve Q. That's what it was identified as right here. So this is curve Q, which is also called f of x. And they're saying that the parent function is being obtained from this one, not the other way around. So if I was going from here to here, then I would say that the stretch factor was at 5, my horizontal shift was +4, and my vertical shift was -72. But we're not going from here to here. The way this is worded, it's saying this one can be obtained from this one. So it's like we're working backwards to get to that. So we're kind of doing the opposite of all that in order to get the values for T, R, and S. So let me kind of bump this down. I'm going to kind of rewrite this one here and then use it on my paper. But we were looking at the 5x minus 4 squared minus 72 for that function. So let me bump down so you can see the rest of this. So again, keep in mind we are going from here to the parent function. So how do I work backwards to get to this look here? They tell us it was 2 transformations, and they give us an order. So I'm going to follow what it says here in the wording. So a vertical stretch factor of t. So I have it at 5. I want it to be at 1. So how do I work backwards to get it to be that? Well, I would have to multiply by the reciprocal of 5 in order to make that happen. So the reciprocal of that is 1/5. So that's the factor I would have to use in order to make this guy look like this guy. And so this is the appropriate answer for t is 1/5, because that's what I have to use in order to create the 1 that you see right there. And so that should be our answer for t. And then it's followed by a translation. So let me just filter that in first. So a 1/5 of 5 we already saw was 1, which is what we were shooting for. And so here's what it looks like now. So now I can figure out what's the translation, what is the horizontal component, and what is the vertical component that's going to get me this look here. So it's kind of like I'm trying to undo this stuff in order to get back to the parent function. So we already figured out t was a 1/5. Now I got to figure out the 2 components of that translation right there. So let's just start with the horizontal component, which is r. Again, keep in mind, if I was going from here to here, we would have said I shifted 4 units to the right, and so my horizontal was +4. But to go back the other direction, now I have to shift 4 units to the left, so my horizontal component becomes -4. So that's the r value that we would have to come up with, because we're going backwards on this. So again, from here to here would have been +4, but we're going back the other direction to get here, so that's why we're going to use -4 for that. And again, we already figured out that was my t value. So last one for the vertical component for s. Again, same thing, we're going backwards to get to the parent function. If you were going from here to here, you would have said that it is -72/5. But we're trying to get back to this look here, so I have to do the opposite and call it +72/5 in order to get that guy. And that was it. That was the end of question 3.